Okay, so I wanted to address these problems from the section 2.7 from Strang's book. So please read the conditions of the problem carefully. In the assignment, I said for 2.6, 4B, B, C, D, F. So those are these ones here. Let's go ahead and mark them up. Let's see, where do we mark up? Come on, help me here. Okay, there we go. I'll take a medium-sized one so I can see one. So we're doing B, and what is the other one? C, D, and F. Okay. Now for these four, is for those implications that fail, give counterexamples to show that the implication is false. So I'm not sure, it wasn't clear to you what to do, but this is what was asked to do. Now, for part B, if we look at, let's look first at part B. If an goes to 0, then an minus 1 also goes to 0. That's, well, that's true. I mean, one way of thinking about it is that this one's going to go to 0, this one's going to go to 0, so they both go to 0. But for B, B implies A is false. But you're supposed to give an example of why it's false. So one example would be, very simple example would be an is equal to 1 for all n. Now in this case, an minus a minus 1 is always 0. Now if a number is 0, it approaches 0. That's a special case. So this is a counterexample to B implies A. I should do it this way. This is implies. Okay. Let's look at C. Now let's see. Here we say A is less than or equal to n, and B is A is equal to n. Now of course A does not imply B. So A does not. I'll just write it this way. A does not imply B. So I want a counterexample. Well, you can just say an. You can just say an is equal to n minus 1. How about that? Okay. That's certainly less than n. Okay. So that's a counterexample. So that's my example. Okay, so that's what I wanted. I want examples for these. Okay, so that's why I put it as a problem that needed details. If I want to do D, well, you can kind of get the idea. So here you said n goes to 0, and B is sine an goes to 0. Now, A implies B, but B does not imply A. And you should give an example. Now, what you should do is you should give an example of an. And one thing I can just show is that certainly if you draw the graph of sine, right? If I take a sequence that goes like this, come on, work with me. Oops, okay, that's just, okay. Suppose I take a sequence that goes, so this is 0, and then this one would be 2 pi. Now, if I take a sequence of points that approach this point here, then that would be an example. Now, the easy way to do that is just say, I could just say an equals pi. That's the easy way to do it. Again, just because it says the arrow there doesn't mean you can't give a simple example where the an's don't go anywhere. Okay, so our arrow just means it eventually ends up there. It can be constant if you want to. All right, so in the last one, F, this one's actually kind of an interesting example because let me see if it's going to go for me. If I take F, if this was an absolute value, here, it would be true. But the fact that there's no absolute value means that it's not true. We have A does not imply B. Let's see. A does not imply B. And the example would be, the example I could say is A as an. One example I could do is minus n squared, all right? Because that's still less than n. The absolute value is not less than n, but the number an is less than n. All right, we also have B does not imply A. Now, why is that true? Okay, why does B not imply A? Well, if an over n converges, then an certainly does not need to be less than n. Let's see if we can think of an example. We could just say, because all we need to do is find one case where an is not less than n. We could say, for instance, an is equal to 4, let's see, 4 square root of n, something like that. Now, an over n converges. Or actually, why don't I just make it easier for myself? I'll just say an is equal to 1,000. Okay. All right, again, I just try to find the easiest one, and this is for all n. Now, certainly a1 is not less than 1. N is not less than n for n less than 1,000. But certainly, an over n is equal to 1,000 over n, and that goes to 0. Okay, so that's the example of this one. So it's asked you to give examples of that. All right, now the next question that we didn't give example. All right, so here I just asked, similar to give an example, it says give an example of a function f of x where the limit f of x is L when x approaches a, but the condition is not satisfied. So we're looking for a function whose limit is L when x approaches a, but the condition is not satisfied, and that's for this one. So what is one saying? It's saying f of x minus L is less than epsilon implies x minus a is between 0 and delta. So what's the picture there? What's the picture there? I have a here. And I have my x minus a is less than delta. That's this interval here, a minus delta, a plus delta. And then I have my L here. And here I'm saying that f of x minus L is less than epsilon. So that means that f of x minus L is less than epsilon means that I have L minus epsilon and L plus epsilon. And the function is lying, basically, when you're talking about limit, you want the function to lie in this box. Sorry, in this box here, where the x limits are a minus delta to a plus delta, the y limits are L minus epsilon to L plus epsilon. Okay, sorry about the junky picture here. But this is saying that whenever f of x is minus L is less than epsilon, then x minus a must be less than delta. Simple example where this is not true is I can just say f of x is equal to L. Okay. Now, in that case, f of x minus L is always less than epsilon, no matter what epsilon is. Okay, so f of x minus L is less than epsilon for all epsilon. Okay, but certainly we don't have x minus a is less than delta. Okay, for any delta. Right? Because I can take, if I choose delta equals 1,000,000, then I can choose f of x equals L plus 1,000,000. I'm sorry. If I choose delta equals 1,000,000, I can choose x is equal to a plus 1,000,001, and still f of x is equal to L. Okay, so be careful about the statement of the problems, and the other problems were fine. So we'll stop there.